In this video, I'm going to investigate the exactness of the differential equation 2x plus y dx plus x plus 2y dy equals to 0. Then go on and solve it if it is possible. A differential equation which is of the form m of xy dx plus n of xy dy equals to 0 is exact if the partial derivative of m with respect to y is equals to the partial derivative of n with respect to x. In the equation that is given, the coefficient of dx there is 2x plus y. For this equation here, the coefficient of dx is the m of xy. So by comparison there, we see that m of xy is equals to 2x plus y. In the given equation, the coefficient of dy is x plus 2y. On this equation, the coefficient is n of xy. So by comparison, we see that the n is equals to x plus 2y. I now go on and evaluate the partial derivative of m with respect to y. So I will be differentiating the 2x plus y here with respect to y. When you are differentiating partially with respect to y, we'll be treating x as if it's a constant. So the partial derivative of m with respect to y, it will give us a 1. We'll go on and evaluate the partial derivative of n with respect to x. We are looking at the x plus 2y here. So when differentiating with respect to x, we will be treating y as if it's a constant. So we'll have the partial derivative of n with respect to x there will give us a 1. So we have those are two partial derivatives. And for that differential equation to be exact, these two partial derivatives must be equal. So in this case, we are seeing that those two partial derivatives, they are equal. They are each having a value of 1. So since they are equal, this differential equation is exact. So if the differential equation is exact, I will now go on and solve that differential equation. The general solution of an exact differential equation is given by f of xy is equals to c, where f of xy is obtained by solving the equations partial derivative of f with respect to x is equals to m of xy, where the m is this one here. And solving the second equation, partial derivative of f with respect to y is equals to n of xy, where the n is this one here. So I now go on and solve for xy using those equations there. As I said, our m is 2x plus y. So substitute it here, we would have partial derivative of f with respect to x is equals to 2x plus y. Our n is x plus 2y. Substitute it here. Then we would have the partial derivative of f with respect to y is equals to x plus 2y. I will then go on and label this equation, equation number 1. Then this equation, I will label it equation number 2. When you are looking at equation number 1 there, for us to get the f, when we have that partial derivative, we have to integrate equation 1 with respect to x. So if we integrate this part, it gives us an x squared. Integrate this part here with respect to x. We are treating y as if it's a constant, so we'd get xy. But our constant of integration, since this was a partial derivative, our constant of integration will be in terms of y. So when we integrate, we would have f of xy is equals to x squared plus xy plus h of y, where that h of y there is a function of y only. And I'll go on and label this equation, equation number 3. I'll now go on and differentiate equation number 3 with respect to y. Differentiate it so that we get a partial derivative of f with respect to y so that we compare with equation 2 there. So differentiating equation 3 with respect to y. So when we differentiate equation 3 with respect to y, for this part here, the x squared, it will just be a 0. This part here, xy, with respect to y, it will give us an x. This part here, differentiating h of y, a function of y with respect to y, it will just give us the derivative of that function with respect to y. So what we would have there is the partial derivative of f with respect to y is equals to x plus the derivative of h of y with respect to y. I'll then go on and label this equation, equation number 4. So we have those equations now. But let us now go on and compare equations 2 and 4 of these equations here. We see that those equations, they have partial derivative of f with respect to y on the left hand side. These parts, they are the same. So if the left-hand sides are the same, then the right-hand sides should be the same. So what we would have there is x plus 2y is equals to x plus the derivative of h of y with respect to y. And then when you look at this equation here, we are having an x on both sides. So if I put it on the other side, it will give us x minus x, it will be a 0. What would remain with is 2y is equals to the derivative of h of y with respect to y. So I can go on and write the derivative of h of y with respect to y is equals to 2y. I then go on and label this equation, equation number 5. We now go on and find the h of y. Find h of y when you have its derivative there. We just have to integrate equation 5 to obtain the h of y. So when we integrate there, the 2y with respect to y. 2y with respect to y, it gives us a y squared. Then we would need to add a constant of integration, and I'll call that constant of integration C1. So we'd have h of y is equals to y squared plus C1, where the C1 is a real number, a constant of integration. I will then go on and substitute h of y there into equation 3. So the h of y that I'm talking about is this one here. We'll substitute it into equation 3 on this part here, where we have that h of y. So when we substitute for that h of y, what we'll get is f of xy is equals to x squared plus xy plus y squared plus c1. So the solution that we are having there for the f of xy is x squared plus xy plus y squared plus c1. And the general solution of this differential equation is given by f of xy is equals to c, where c is an arbitrary constant. So we have our f of xy here. So the general solution will be x squared plus xy plus y squared plus c1 is equals to c. So we have that equation there. But C1 here is just a constant. The C is a constant again. So I can try to put that C1 on the right hand side. Then we can go on and rewrite the equation as x squared plus xy plus y squared is equals to C2, where C2 is the constant which we obtain when we subtract C1 from the constant C. So what we are having there, this part here, that's the general solution of this given ordinary differential equation.